dedicated or dead. All right, that's it. So that illustrates also this very nice phenomenon of the lowering of the resistance of this ring. As we once talked about, the resistance as a function of temperature does go down with temperature set. When I try to put current through that, a lot of current goes through and it makes a nice big fat magnet falling down. What else do we want to do? Oh, well, today we did want to actually go over this one other cute experiment. The point being that there are various ways of changing this product of B and A. You can change B, you can change A, and you can change the angle between them because it's the flux. You know, the flux has to go through an area, so the flux is this, the field is this way and the area is this way. There's no flux through the area, so you can vary the angle. Okay, well, so here's the story. What we do in a generator is we're actually changing the angle because you saw, for example, in this little model here, the coil, there's a magnet here, but the coil changes its direction. So we're changing the angle. B is okay, B is constant, area is constant, but what we're doing is we're changing the area so that we're catching different amounts of flux through the loop. So we're changing theta in that case. And that's the way the electric generator works. We are changing theta by turning a coil inside a magnet. And you can analyze that. I don't have time to do it, but you can vary the angle and so on and so on, and you can actually do the math on that. That is, the magnetic flux B times A is BA times the angle between the field and the area. So, and if theta is changing in a sinusoidal way, namely you're just turning it at a constant rate, you get dB, dA times this cosine will give you the electromotive force. This is strange. I don't know why it doesn't show the curly epsilon. That should be an electromotive force. All these computers give a different answer. In any case, when you take that derivative, what you bring down is the rate of change of the angle, which is omega, is the angular speed, the number of 2 pi angles you turn in a second. So when you get it all done, the electromotive force will be, again, this electromotive force, if you have n turns, you will get that the maximum electromotive force is the rate at which it turns, the number of turns, the strength of the field, and the largest of the area. But this is due to the angle turn. So my way of remembering this is that the electromotive force is the, again, a women's analogy, Women's National Basketball Association. And that's the electromotive force by a generator. Okay, now you can get the same answer by looking at it from the force point of view. Oh, and here the little curly E came out nice. I don't know why it didn't. So, and again, just doing figuring out the force acting on this loop, you can get that the electromotive force is the WNBA. Oh, that's omega, not W in fact. Okay, so we saw that the electric motor and electric generator are basically the same structure. In the one case, we put electricity in. We put the electricity in. We put it in a magnet. The fact that there's electricity going through, current, that current is acted on by the B field, and you get a force. And the force will turn the loop. So that's a motor. On the other hand, with a generator, we start with no current in. We don't put any current in, but we turn the loop. And in so doing, we change the flux passing through the loop. Or you might think of it as the electrons are moving with a velocity across the field, and a force acts and current comes out. So that's the difference. It's the same structure. It's just in one case you put in current and you get out the turn. But the other case is you turn it by force. And of course, it will resist you, and you get voltage current coming out. So let me continue with a different. Yeah, this one. And let me view it properly. Okay, now I want to catch up to where we are. So that is the theory of how, when you change the angle, you have the possibility of making an AC generator, which is what's going on. Apparently there's some AC generators, probably diesel operated. Instead of one of these hot things here, you probably have a diesel engine turning a coil in a magnet, and that's lighting up to an L hole. So we have that. Now the other one that I wanted to show you, because you've done nuclear magnetic resonance, but nuclear magnetic resonance can be viewed as this kind of magnetic phenomenon. Oh, I have about 5 minutes to do this, so I think, where did I put that? Here. It's somewhere next to my wallet. Ah, top. This is very amazing thing. The nuclear magnetic resonance was invented around 1946, just after the war. There were two groups. One was at Harvard, and one expression was at Stanford. They both had the idea that you could use the magnetism of the nucleus and pick it up and actually measure the magnetism of the nucleus, which is really a hard trick because nuclear magnets are very, very small. Now, they approached it from different ways. I don't know if you had an explanation in terms of energy levels and resonance. So that's one way of looking at it. This is the Harvard view, where you take a magnetic moment, a magnetic dipole, and you put it in a magnetic field. And it turns out quantum mechanically that if you have hydrogen, it will either be pointing parallel to the field or anti-parallel to the field. It's quantization known as where we'll get to that in a little more detail if you haven't seen it already. So there'll be basically two energy levels. The lower one is when the magnetic moment is parallel to the field. So this would be the parallel case, and this would be sort of the anti-parallel case. This is an interesting thing we should talk about more sometime, is that when you have a magnetic field and you have a magnetic dipole, the magnetic dipole will line itself up preferentially with the north going along the lines, because after all, this field that you put it in started out at some north pole someplace, and the lines are going this way, and this guy wants to get away from the north pole, so he will align himself in that direction. And that's a low energy direction. The high energy direction is when it's the other way around, when the north is this way and south. Clearly he doesn't like it as much, so you have to do some work to turn this around, and so on. So you have two energy states. This is the parallel state, lower energy, this one, and this is higher energy. So that's how Harvard people look at it. It's quantum mechanics, and then what you do is you shine in radio frequency energy, and you cause the magnetic moment that was this way, you cause it to flip over this way, because you have to give it energy to make it go in this unfavorable alignment. So that's one way of looking at nuclear magnetic resonance. Now the Stanford idea was by a man by the name of, well, I should say who this was. This was Purcell, whose book I recommended to you, and he shared the Nobel Prize with this other gentleman, Bloch, at Stanford. who took a very simple approach, and that's what I want to show you. He said, if you have a nuclear moment, it also has angular momentum, which we'll talk about. And if I can make this magnetic moment precess, it will send out magnetic field, and I can pick up that magnetic field. So you do something like this. The motion he's talking about is this wobbly motion. And if you can imagine that wobbly motion is a north pole going around, you see the north pole faces this, and sometimes it faces away, so it's creating a varying magnetic field through this loop. So it can induce an electric current in this loop, which you can then pick off and tell that I have a spinning magnet in here. This angular momentum is a very cute thing, because if the thing isn't spinning, it falls right over. But if it is spinning, it just stays, because that's conservation of angular momentum. The thing wants to maintain a certain axis, and as it wobbles, it sends whoop, 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 changing magnetic field. So Bloch's method is, he has two coils, one in which he drives this thing, makes it wobble, and the other one he picks it up. So it's a I don't know if you've done NMR, whether you've used the two-coil method or the Purcell method. You can use one coil, because he measures something slightly different. But this is a beautiful example, I think, of a changing magnetic field picked up, and I think I even quote, I quote Bloch, his Nobel Prize address. The rotation of our compass needle, meaning that rotating spin, is accompanied by that of a magnetic field which possesses an alternating component perpendicular to the axis of rotation. It's rotating this way, but perpendicular, it's got this component of magnetic field, and hence by an electromotive force induced in a suitably wound coil of wire around the sample. So you just wind the sample, a coil around your sample, and as this wobbly magnet comes around, it induces in here. Son of a gun, you want a Nobel Prize, you deserve it. I mean, it's great. It's not as though Bloch doesn't know quantum mechanics. I mean, he did fantastic things with quantum mechanics, but he had this simple view of how to handle this. Okay, so I think that's about all I wanted to say. We have 10 more minutes, but one thing I did want to do, for those of you who stuck with us so long, is talk for a minute about Michael Faraday. Now, oftentimes I like to remember the birthdays of great scientists. We missed his birthday by a couple of weeks because we weren't quite up to his great discovery. But he's one of the great scientists. And I quote something where he said how often he had an idea, he tried it, it didn't work. So this is his comment, which is inspiration to those of us who fail trying. Keep going. He says, they just don't know how often you try, and you just don't. Your hopes, your wishes, and not a tenth of those suggestions have been realized. So he tried many, many ways and many times to get this effect. But his life story is very interesting. I don't know if you heard about his life. Well, he's an English kid, and he was a poor kid, and he could go to school only until he was 14. And then he was apprenticed to a book binder. In those days, a bookstore, you'd actually paste the pages together. The difference with Michael Faraday was he also read the books. And he was very interested in science. And in those years, they had public lectures. They'd have some great scientists come and give a public lecture. And so what he did, he took his notebook and he went to the lectures of Sir Humphrey Davy, who was a great chemist, renowned English chemist. And he wrote down Davy's lectures very carefully. And in his bookbinding way, he bound them all together. He made this wonderful presentation. He brought it to Davy and said, look, I'm very interested in this work. Could you give me a job? And Davy said, I'm sorry, I don't have any work for you. But apparently, then a little while later, Davy had an argument with his assistant, fired him, remembered the kid with the book, and looked him up and hired him. And he said, okay, I know you can take notes. Why don't you just follow me around, shadow me, as the expression goes nowadays, and write down what I say so that I can then have my notes and publish them, that sort of thing. So Faraday did. He was a dutiful guy. He wrote everything down. And he accompanied him, but in the meantime, he's learning. And before long, he had his own ideas. And he started doing some experiments on his own on the side. Great ideas. Davy was a little bit worried about this, because who was this lowly kid doing with ideas, So he started to publish his own work. And this is 1820. This is when Ørsted did his discovery. So then everybody was trying to generate electricity from the inverse of Ørsted's effect. By 1830, Faraday had done it, and he published. Up to that point, it's very funny. He had been accompanying Davy, for example, around Europe and meeting some of the great scientists in Davy's wake, behind him. The story is told that Davy's wife was so uppity that she wouldn't have dinner with him. He had to eat with the servants in the kitchen while they dined with the visiting, the scientists they were visiting. So he put up with all that, and he did remarkable work. I mean, not just invented the electric motor, the electric generator. He did electrolysis. There's a Faraday constant in electrolysis. Have you come across that? He discovered the polarization of light when it reflects off a magnetic material. It's also called the Faraday effect. And he discovered diamagnetism and paramagnetism. But he declined the presidency of the Royal Society. He wasn't that proud. And he refused to become a knight. Good man. My kind of guy. What I'd like you to try is for each of you to come up and do this little experiment. Please come up orderly and line up. Turn the thing. There's a sign here. Turn it this way. Why don't you come up, if you like. And the other thing, while the rest of you are occupied, we're going to celebrate Mr. Faraday's birthday a little bit belatedly. We have some cookies. So come on up. Happy birthday. I don't have any cookies. Why they name them after Newton, I don't know, but Faraday's just as good as far as I'm concerned. So come up and have something while you're waiting. Please keep you busy while you get strength to do the other experiment. Oh, yeah. You're welcome. There was some society that he joined. It was called Sandeman or something like that, so that's a little bit like that. Please go ahead. Sure. Pardon? You can grab two. Hey, so the trick here is, did you do the whole thing? And you feel that difference? Oh my God, is it never? Oh, and the other thing I wanted to show you is the Lenz's law thing, where if you get it going with high speed, yeah. All right, now you'll see that it breaks. Go ahead, hit it. That's called regenerative braking. What they do in the Prius, for example, you're riding along, your wheels are turning, so you got a lot of kinetic energy. Then if you hit the brakes, it connects to a generator, to a battery, and they use the turning of the wheels to regenerate electricity to charge the battery. So you don't throw away all that energy of the motion. So that's what helps to make the Prius really efficient, because you don't throw away the energy in the braking. It's called regenerative braking, and I think some American cars are doing that too. So let's both. You want to try both of those things? You want to try? Okay. You want somebody hit the button for her? No. Oh, that's for braking. Okay.
I can actually go more.
Go ahead. You think so? And then, I'm telling you. Go ahead. It's a strong man. Oh, yeah, go ahead. All right, so you want to hit the button for him? Go ahead. No, keep it down. Keep it down. Now you'll appreciate it. You need some more cookies, I think.